So today we're going to learn about vectors as forces. So I'm not going to read over all of this. You can do so in your notes. But basically, a force can be applied by pushing or pulling on an object. Okay? And what happens is that initiates the motion, so it speeds up or it slows down. So there is one single force that has the same effect of all of the forces acting together on the object, and we call that the resultant. So for a quick example, I'll take you over here. So if we have an object and it has one force acting in one direction, another force acting in a separate direction, the resultant force is what we would call, so if we do our parallelogram method, we know that this vector here in black is the addition of these two, and we call this R, or the resultant. So although there are two forces acting on this object, we can think about it as having one single force, the combination of the two blue forces that act in the direction of the black vector that you see there. So as I just finished saying, the resultant is the vector sum. So we know how to add geometric vectors and algebraic vectors by this point, so we'll be able to use that information we know to help us with this unit. So this entire paragraph is a whole review of forces. Those of you in physics, if you're not taking physics, you want to read this carefully. Pay close attention to where it talks about equilibrium. So equilibrium is the state of rest, or it's the state of uniform motion. So if you're at constant motion, you're in equilibrium. So if you're stopped at a stop sign, you're in equilibrium. If you are on the 401 with your cruise control set at 100 kilometers an hour, you are also in equilibrium. You're neither speeding up nor slowing down. Okay. So what happens with this equilibrium force, so we call it the equilibrant, okay, is the force that is equal to the magnitude of the resultant force. We just talked about the resultant, but it is in the exactly opposite direction. So it works exactly against the resultant force. So if you focus in for a second on this diagram right here, we can see that we have one force, F1, acting one way, F2 acting another way, and the overall resultant force, which is the addition of these two. So our resultant force here, okay, is what we have, the combination of those two forces. So we call our equilibrant force its exact opposite, same magnitude, but going in the exact opposite direction. So we also see another example of that below. So moving on to the next page, just a quick little definition of equilibrium. So when we're dealing with three vectors, so we have three non-collinear vectors, okay? So this is the example with the non-collinear vectors, hence not parallel. The example below, we'll talk about it in a minute, that's the example where they are collinear. So we were in a state of equilibrium if the sum of these vectors is the zero vector. So they produce nothing in the end. So we see this here. And what you'll see geometrically when you draw these vectors, you're going to see a closed triangle. Okay, if three vectors are in equilibrium, they're going to close the object. Same with 10. If you have 10 vectors in equilibrium, it will create a closed decagon. Example 2 talks about if we have collinear vectors. So what you can see is that this vector A and the addition, this vector B that's going in the same direction, and then vector C is exactly the magnitude of these two, but going in exactly the opposite direction. So you can think of these as canceling each other out, otherwise known as producing a zero vector. Moving on to components. Every vector, or sorry, every force is going to have two components to it. It's going to have a horizontal component and a vertical component. So I'm going to do a quick little diagram over here. So if I have some sort of force going this way, this has this is what we think of this as the combination of two forces acting not only in the horizontal direction, but also the vertical direction. And there's also an angle that's created with the horizontal, otherwise an angle of elevation, if you will, if you're thinking of this in realistic terms. So if we look at this diagram here, okay, what's happening is we have a force F that we can see here. So we have one overall force, and we have this F subscript X traveling in the horizontal direction and F subscript Y traveling in the vertical direction, and the angle theta marking the angle between the resultant force and the horizontal. Now we want to figure out what F subscript X is, as well as F subscript Y, in terms of the F and the theta that we know. Okay, so we're going to use SOHCAHTOA, and we realize that the cosine of theta is adjacent over hypotenuse. So that means the cos of theta is going to be the adjacent side that we see here divided by the hypotenuse. So we have F subscript X divided by the overall vector F. And a quick rearrangement, we're going to take the F and we're going to multiply it up here, and we end up with the force in the X direction, or in the horizontal direction, is equal to the overall force times the cos of theta. And if we go up a little bit higher, we're going to see that right above in our triangle diagram here. So we have the horizontal component as the overall force, okay, the magnitude of the overall force times the cos of theta. Yes, I should also mention, apologize, everything here should have had a magnitude sign on it. Please do not make this mistake, okay? The cos of theta is the adjacent over the hypotenuse, which are side lengths only, which means we must take the magnitude of the vector only, okay? Please don't make that mistake as I just did. With a very similar method, it's this time using sine theta is opposite over hypotenuse, you will come up with the fact that the vertical component, or F subscript Y, is the magnitude of the overall force times the sine of theta. So here we are. We know what the horizontal component and the vertical component of any vector are now in terms of the overall force and the angle theta that's made with the horizontal component. So now we're going to use this information to move on to the next example. So please click on the next video for the following.